it's really time in the course to start thinking of variables as having distributions rather than simply an individual observation being the only thing of relevance. In other words, if we choose some random variable x, and to use the example in my notes, the number of heads when you flip a coin 4 times, that variable can take on more than one value, and in fact we don't know which of those values will occur first on the first 4 flips of a coin, or what would occur the second time. It may be the same thing that occurred the first time, and so on. So the idea of a probability distribution is to sort of lay out the possibilities. In other words, what are all the possible values the random variable can take on? What are the probabilities of those values? Well, as we said, the coin was a fair coin, so let's think about this for a second. If you're going to flip a coin 4 times and it was a fair coin, how many heads would you expect to get? And the answer is not very difficult to come up with. In fact, it's the mean of our distribution. It would be 2 heads. So on a fair coin, we would expect 2 heads to occur more often than the other outcomes, but we would also not be surprised if we saw an outcome of 1 head in 4 flips or 3 heads in 4 flips. In fact, we would think those would be equally likely, 1 less than the average, 1 more than the average. It's also possible to get 0 heads in 4 flips, but as you might imagine, we don't expect that outcome to occur very often. And we also would not expect to get 4 heads in 4 flips. But we also realize that we'd expect that 0 heads would be equally likely as 4. So if you draw this out, and we did on the table, you can look at the probability that we came up with, but more important from my standpoint is recognize what this distribution looks like, that it actually has a shape, and it's not a surprising one. We'd expect a peak at 2 heads, the outcome that occurs more often. We'd expect that 1 and 3 heads would be equally likely, but that they would not be as likely as 2 heads, and that 0 and 4 heads would be equally likely, but not as likely as 1 and 3. So if you sort of picture this in your mind, or draw a picture of it on a piece of paper, what you see is a symmetrical distribution. Single peak, mean, median, and mode the same, symmetrical in the sense that if you folded that distribution in half on a piece of paper, that the 2 sides would lie right on top of each other when you folded the paper. So a symmetrical distribution is not a surprise in this case. We'd expect it, but I want you to consider something else. What if it wasn't a fair coin? What if it was only a probability of 0.25 of getting a head, or 1 in 4 flips would give you a head? Well, what you'd recognize right away is if that was the case, 1 head would be the most likely outcome, and that 2, 3, 4 heads would be less likely than 1 head, and that our distribution would be not symmetrical. It would not be a symmetrical distribution like the previous one, but in fact would have a right skew. It'd have a long right tail in this case, not terribly long because we've only got a few possible outcomes that we've got in this case. But what you find is that when the mean is not at the center of the distribution, and that single peak is not at the center, that you get a right skew if the highest point is on the left side of the distribution. Well, if we thought that there was a 75% chance of a head, you sort of pretty quickly understand you've got a left skew in this case, that the most likely outcome that would occur, our expected number of heads, or our mean distribution, would be 3 heads in 4 flips, and that it would be less likely to get 2, 1, and 0 heads. So not all distributions are symmetrical. Normal distribution certainly is a symmetrical one, but not all distributions are symmetrical, and that you need to start thinking about the shapes of the distribution. As you might imagine, if the distribution is not symmetrical, the variance would be affected by this, as would the standard deviation. Now, I went through those calculations in the notes, and I'd also be the first one to tell you that on a real probability distribution, we probably wouldn't be calculating the mean or the variance or the standard deviation. In other words, if there were hundreds of possible outcomes, or theoretically thousands or even infinitely many outcomes on a continuous distribution, the calculation is essentially impossible, and that we'd have to either do this via computer, or that the information has to be given to you like the problems that we do in class. So the truth of the matter is that the example I used was actually a very simple one with a discrete random variable that made all our calculations much more easy to undertake than it would be if we had a true continuous random variable. But the reason you start out with a discrete distribution is because it's easier to draw, easier to put together a table, and a lot easier to visualize as you work your way up to a continuous distribution and all the possible shapes that those distributions can take on.